Did you realize we are pretty close to the end of the semester? Yeah? So, including this one, could it be that we have only 5 lectures to go? Okay, so, yeah, I was a bit surprised. So, okay, so here's the plan. The plan is today we are going to talk about some important probability distributions. And in the context of these distributions, I'll talk about expectations, variances all over again. Okay? And then for the next 2 lectures, we'll talk about continuous probability distributions, inference, that sort of thing. Okay, sorry, can we... There's somebody whose voice really carries, so... It's just you're the resonant frequency for this room. Okay, and then we'll final couple of lectures, we'll talk about infinity and about uncomputability, Gödel's theorem. Okay, so that's the plan. Okay, okay. So let's talk about what these interesting probability distributions are. So there are going to be 3 of them. Okay, these are the 3 distributions you'll see most often among the discrete distributions. So we'll also talk about continuous probability distributions later. So the 3 are, one we've already talked about. It's called the binomial distribution. Right, so you toss a coin n times. And our random variable x is the number of heads. Okay? So the probability x equal to k is just n choose k, p to the k, q to the n minus k. The expected value of x is just n times p, right, by linearity of expectations, by linearity. The variance of x is equal to n times p times q. And this was because x was equal to x1 plus x2 plus so on up to x sub n. And the x sub i's are independent random variables. Right? Remember what it meant to say that the x's are independent random variables? We say that x and y are independent if probability x equal to j and y equal to k is the probability x equal to j times the probability y equal to k. So all the events about x and y are independent. Right? So given random variables x and y, what are the events? The events are x equal to something and y equal to something. And these events are independent. Right? So for all j and k. Okay, and so the standard deviation, which is the square root of the variance, was just square root of n pq, which is about square root n. Right? It's smaller than square root n over 2. Okay, so that's what we saw about the binomial distribution. we know what it looks like. It's so if you plot it, the number of heads lies between 0 and n, and we expect it to be n times p, and the distribution function sort of looks like that, right? Actually, it looks, I'm being far too conservative here. What it really looks like is very, it's very, very peaked. So it's almost 0, and then it sort of shoots up, and then, oops. Okay, well, let's try again. So it shoots up, and then it comes down. Oops. Okay, well, that'll have to do. Right, so it's almost 0, except for this, this small place where it shoots up, and then it achieves its maximum, and you might even think of it as having a little plateau of about square root of n. That's what it looks like. Okay, not quite a plateau, but approximately, right? So it's, that's what it looks like. Yes. Yes. All right. Okay, so that was one of our interesting probability distributions. It comes up all the time. So why does it come up all the time? Because, almost, many things can be thought of as tossing a coin n times. Right? When you're sampling from when you're doing sampling to figure out, what you're polling a population, it's like tossing a coin many times. It just keeps coming up in many situations. There's another distribution that comes up, which actually all the three distributions we look at today correspond in some way to tossing a coin. So the second distribution is called the geometric distribution. Okay, geometric meaning not geometry. Geometric meaning, think of it as a geometric series. Right? Okay, so what's the geometric distribution? It's basically you're tossing a coin. So you have a coin, probability of heads equal to p. 1 minus p equal to q. And now what you want to know is how long do you have to wait? Sorry, can you keep it down up here? Yeah? Okay, so the random variable we have is how long do you have to wait till you see a heads? Okay, so waiting time for heads. Remember, we called this something. So we called it W1. Right? This was our random variable. And so what's the probability W1 equal to n? So if you have to wait for n tosses before you get a heads, what must happen? Yeah, so it's tails for n minus 1 times, and then it's a heads. So the probability of that is exactly q to the n minus 1 times p. Yeah. Okay, so now suppose we wanted to compute the expected value of W1. Okay, so what's this? Well, so it's just the sum over all n of n times the probability that W1 equal to n. Which is just the summation n equal to 1 to infinity of n times q to the n minus 1 times p. Okay. So now there's a question: how do we figure this out? Okay, so I'll show you two ways of doing this. Okay. So to do the first way, we are going to rewrite what it means to, what's the expectation of a random variable. So for the first way, let's assume that x is a non-negative integer random variable. Meaning, it's a random variable which can take on only values which are non-negative integers. So it's an integer random variable, but the probability of it being negative is exactly 0. So now, here's how we can write. Okay, and let's let p sub I be the probability x equal to I. Okay? So now, the expected value of x is just sum over I of I times probability x equal to I. Okay? So it's sum over I of I times p sub I. So I equal to 1 to infinity. Well, 0 to infinity. Okay, but 0 you can leave out, right? Because I equal to 0, then this term is 0. So it's P1 plus P2 plus P2. Yeah, 2 times P2 plus P3 plus P3 plus P3 plus P4 plus P4 plus P4 plus P4, and so on. Okay? So now if you look at this, this is equal to the probability x is greater than or equal to 1 plus that's equal to the probability x is greater than or equal to 2 plus probability x is greater than or equal to 3 plus dot, dot, dot. Yeah? So in the case that x is a non-negative integer random variable, you can compute its expectation by taking the sum of the probabilities that x is greater than or equal to I. Right? So this is summation I equal to 1 to infinity. Probability x is greater than or equal to I. Okay, so we can go back to our problem from before. So we want to compute the expectation of W1. W1 is a waiting time for something. It's non-negative. Right? You have to wait for at least 0. You can't wait for negative time here. So the expected value of W1 is the sum over n, sum over I, equal to 1 to infinity of the probability W1 is at least I. Now, what's the probability W1 is at least I? Yes?
The probability that the first I point turn up the tail.
Yeah, the probability W1 is at least I is the probability that the first I minus 1 coin flips turn up tails. Right? You know that you have to wait at least I turns. So the least that must happen is that the first I minus 1 are tails, and then you might stop at I because you got a heads. But that's the first time you could possibly have gotten a heads. You may not yet, because we are saying it's greater than or equal to. So this is just q to the power of I minus 1. Okay? So this is, if you want to write it out explicitly, it's 1 plus q squared plus dot, dot, dot. So it's a geometric series. Hence, the geometric distribution. Right? It's a Okay, so this is 1 over 1 minus q. 1 minus q is p, so it's 1 over p. Okay, so sort of makes sense, right? I mean, it's the nicest thing we could have expected. So if the probability of heads is 1/3, how many times do you expect to flip the coin before you get a heads? It's 3. Okay. Let me show you another way to compute this answer. Okay, it's a perfectly valid way of doing it. It'll seem like a trick, but to really make it, to know that it's correct, you have to know about conditional expectations. But it's sort of intuitive, so I'll show it to you anyway. You can see, but you may not be able to formally justify it, but it's good for you to at least see what the trick is. So we want to know what's the expected value of W1. The expected number of times you have to wait till you get the first heads. So what is this? It's 1 times the probability that you get a heads in the first term, which is P. And then what if you don't get a heads in the first term? Okay? So if you don't get a heads in the first turn, then remember this coin is memoryless. There's no memory in the coin. Okay, so let's. It's not an emergency, I hope. Okay. We don't need to evacuate, I hope. You okay? Okay, good. All right. Okay, so, all right. Do we need a break, or should we get back to W1? Yeah, get back? Okay. Okay, so here's a slick way of computing what's the expected waiting time for the first heads. Okay, so you say, well, the expected waiting time for the first heads, well, with probability P, you get a heads in the first term. Right? So suppose not. Suppose you don't. Well, then, how long do you have to wait now? There's no memory, right? So it's as though you're starting from scratch. Right? So with probability 1 minus P, how long does it take you? Well, it already took you 1 turn. And how much longer do you have to wait? Expected value of W1, right? Because you're starting from there. You already spent 1 turn, and now how long do you have to wait? Well, you have to wait expected value of W1 many steps. Okay, so now let's compute this. This is P plus 1 minus P plus 1 minus P times expected value of W1. So you cancel that over, okay, you move that to this side, you get P times expected value of W1 equal to 1. So expected value of W1 is 1 over P. Okay? Yes? Okay, how did I get the first line? I said, okay, so what's our process? We are flipping a coin, and we keep flipping it until we get a heads. So now, let's flip it just once. Either we get heads, then we are done. And so that happens with probability P, and we waited for 1 step before we got heads. With probability 1 minus P, we got a tails. Okay, so that's 1 minus P, and now how long do we have to wait till we get a heads? Well, we already waited 1 step. Nothing happened, we got a tails, right? How much longer do we have to wait? Well, we are starting from scratch. We are going to be flipping a coin until we get a heads. So how long do we wait? Expected value of W1 steps. Okay, so with probability P, we waited 1 step. With probability 1 minus P, we have to wait 1 plus expected value of W1 steps. Right, so now we sort of, so we get P times expected value of W1 is 1. That's Yes?
Why is it 1 plus expected value of W1 and not just expected value?
Well, because see, with probability 1 minus P, how long did we wait? Well, we took the first step, it gave us a tails. We had to wait for that. And then after we are done waiting for that first step, we have to wait some extra time. And how long? Well, expected value of W1. So it's that much time. Is everyone good with that? Okay, so at this point, you should just think about this intuitively. It's actually the case that you can back it up formally. It's a conditional expectation. So, well, what happens when you back it up formally? Then you know that doing this is okay. So that's doing it formally. Once you know how to do it, the fact that you can do it formally, you know that if you make this maneuver, you're okay. It's all fine. You didn't do anything else. Okay, so now let's do one more thing, and then we'll stop for a short break. So it's called the coupon collector problem. Okay, so the story behind this is this. I don't know if they do this with cereal boxes anymore. Probably one of you knows, but it used to be the case that in cereal boxes you would, or in some kind of boxes, I don't know which kind of boxes, every time you'd open the box, a new box, you'd see, you'd get a baseball card or something, some collectible item, and there were maybe n different types of, so there were cards corresponding to each player, and there were n such players, and so these were just rudimentary attempts to get people to feel excited about opening their cereal box or purchasing one, okay. But the coupon collector problem asks this. So suppose there are n different types of cards, and let's say they were equally likely. Okay, which was also not the case in practice, but let's assume they were equally likely. And you wanted a full set. Okay, so how many boxes of cereal would you have to go through before you collected a full set? Right, so again, this is a random variable because you could be very lucky, and every time you open up a new box, you get a different card, and so you need only n trials. But of course, it may not be, and it could be that you got n-1 distinct ones, and then you just had to wait forever before you got the last one because you kept getting these first n-1 over and over again. So x is the waiting time before you collect all n types of cards. So if you try to write out the probability distribution function of x, it's pretty complicated. Okay, so if you try to figure out, but on the other hand, it turns out we can compute the expected value of x very easily. Okay, so what we can do is we can figure out the expected value of x. And the reason, whenever somebody makes a statement saying, well, we don't really understand this distribution, but we can write out the expected value. We can compute the expected value. You know that what's going on here is, linearity of expectations. It's just an extremely powerful tool, right? It's so powerful that even when we don't understand what we are talking about, we can actually calculate the answer. Okay, so what we need to do is figure out how to decompose x as a sum of random variables whose expectations we can compute. Okay, so we want to write x as x1 plus x2 plus ... plus x sub n. The only question is, what is x sub I? What should x sub I mean? to get the, and what do we mean by the ith card? Ah, okay. So here's one thing. Here's one thing you could do. You could say, let's number the cards from 1 through n. So I don't know any players' names. Soccer players, yes, but baseball players, no. So okay, let's see. Barry Bonds. Let's say one of the first, number 1 was Barry Bonds, and then from 2 through n we don't know. There are some names, right? So we number them 1 through n, and then we say, what's the waiting time till we get the ith one, right? So that's x sub I. But then is x equal to x1 plus x2 plus so on up to x sub n? No, it should be the max of x sub I then, right? So if that's how we define x sub I, then x is the first time you see everybody, right? Which is going to be the max of x sub I. So we want to define x sub I in some other way so that it's a sum.
X sub I is the amount you have to wait to get I distinct cards?
Okay, so that's almost there. So you could say x sub I is the waiting time before you get I distinct cards, before you have I distinct cards. And now is x equal to x1 plus x2 plus so on up to x sub n.
Or the time, like x1 is the time to get one distinct card, x2 is the time you waited from the first distinct card to get the
Okay, good. So what we want is x sub I is the time you had to wait from the time that you got the I minus first card, from the time you had I minus 1 distinct cards, up to the time that you got one more distinct card. Right? It's the waiting time to get the ith distinct card from, Okay. So what we have is x sub I. Okay, actually, maybe it's better if I draw the figure. So the figure is like this. Here's time. Here's time 0. And that's where you got the, these are the events. These are the places where you saw maybe distinct cards, right? So what we'll say is that's x1, that's x2, that's x3, x4, etc. Right? It's how long you have to go between having got the last new kind of card. So every time you see a new card, one that you've never seen before, it's an event. And then you say the waiting time from the previous such event to the next one is xi. Okay? So now, what's the waiting time for the first card? Yeah, x1 equal to 1, right? Because the first day you open up a new cereal box, you've got, it's a new card that you've never seen before. Okay? And then what about x2? Yeah, how do you get that? So what's the process you're going through to pick out x2? I'm sorry? Yeah, okay. So it's the probability of getting any other card. Okay, so there are n different cards, and there's one that you don't like anymore, but any of the other n minus 1 are okay. So it's the same thing as though you were flipping a coin, right? Where the chance of getting a heads is n minus 1 out of n, and the chance of getting tails is 1 out of n. Right? If you got the previous card, then call it tails. If anything else, you call it heads. So it's as though probability of heads is n minus 1 over n. So now we want to know what's the expected value of x2. So x2 is a random variable, right? We don't know how long we have to wait till we get the second card, right? But we know what the expected value of x2 is. It's just n over n minus 1. What about x3? So x3 is like flipping a, so now there are two cards which you no longer like because you already have them. But any of the other n minus 2 are okay. Right? So it's as though you're flipping a coin with probability of heads equal to n minus 2 over n, meaning that the expected waiting time x2 is n over n minus 2. Okay? I'm sorry? Oh, this is x3. Okay, so if you continue this, you'll see that expected value of x is 1 plus n over n minus 1 plus n over n minus 2 plus so on and so on plus 1. Oh, sorry. 1, what I meant to write here was plus n. N divided by 1. Actually, this 1 we can also write as n divided by n. And so what you get is n times 1 over n plus 1 over n minus 1 plus dot 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 plus 1. Okay? Usually this series is better written the other way around. So this is n times 1 plus 1 over 2 plus 1 over 3 plus dot 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 plus 1 over n minus 1 plus 1 over n. Okay. So now this series very quickly converges to something very close to log n. So this is approximately n times log to the base e of n. Log n to the base e, right? The natural log of n. Now, if you want to sort of be convinced about this, okay, so actually this converges to log n very, very quickly. It converges to something like log n plus log of n to the base e plus something like a half or 0.57, something like that. But it converges very, very quickly. For very small values of n, it's almost exact. And the reason, one way you can see that this should converge to something like log n is you plot it out. So let's say we start at 1. Okay, so 0 was back here, but we plot starting from 1, and this is 1, and here's 2, and we want a half, and at 3 we want 1/3, and at 4 we want 1/4, and so on. Okay, so so now let's look at a continuous version of this. So let's look at the curve 1 over x. So y equal to 1 over x. So that curve looks something like that. Okay, sorry. Something like that. Okay? And okay, so now what do we want? What we'd like is this area. Right? That's the area that we want to estimate. That's this summation all the way out to n. Right? All the way out to n. What we can do is we can integrate 1 over x. Right? And that will give us the area under this black curve, which is pretty close. It misses only a small amount, which is this constant that I told you about. Okay, so if you integrate 1 over x dx from 1 to n, you get log n to the base e between 1 and n, which is log x to the base e, which is log n minus 0. Okay, so as you can see, the blue area is just a little bit more than log n. That's what it's log n plus a half or 0.6 or something like that. Yeah.
Isn't that the harmonic series?
It is a harmonic series.
So doesn't the harmonic series diverge?
It diverges, yes. But that's what we're saying, right? It diverges because as n tends to infinity, this will tend to infinity. So this log n is the overhead you have to pay, right? So if everything was going perfectly for you, you'd get a distinct coupon every day, and in n days you'd be done. But this is saying, no, it'll take n log n days. So you have to pay a penalty, but it's not very large. Okay. Okay, so how are you doing on stamina? Oh, yes, sorry, question. Yes. This one?
Yes.
All right. Maybe shall we take a minute's break? I'm sorry?
How do you get the BH over n minus 1 over n?
Oh, the probability of heads was n minus, because what we said is that there's, okay. Okay. So let's see. I thought I'd spend a few minutes going over an example for linearity of expectations to show you pictorially why linearity of expectations works, right? Not just the proof, but sort of giving you a intuitive sense of what's going on here. Okay. So that's what we are doing now. It's linearity of expectations. So here's the example we are going to work on, which is the number of fixed points in a random permutation. Right? Remember this example we had about homeworks and people, and we hand back to a random person, how many people get back their own homework. And so we said, this is the sample space. There's probability 1/6 that everybody, all 3 people got back their homeworks. There's probability 1/3 that only one person got it back, and probability, sorry, one half that only one person got it back, and probability 1/3 that nobody got it back. And so if you work out the expectation, the expected value of x is, 3 plus 1 plus 1 over 6 is, right, is 1. Right, so the expected value of x is 1 over 6 times 3 plus 1 plus 1 plus 1. Right? Which is 1. Okay, so now here's how linearity of expectations works. So now what we do is we instead find nice random variables. So we write x as the sum of x1, x2, x3. So what's x1? x1 is 1 if the first person got back their homework, right? So we have a random variable corresponding to each person, and each person is only keeping track of his own homework, or her own homework, right? So x1 says, did I get back my homework? Yes, yes, no, 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 no. Right? x2 says, did I get back my homework? Yes, no, 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 yes. x3 says the same thing, and it's yes, no, yes, no, no, no. Okay? So now, let's see. What did we do when we computed the expected value of x? We really computed the sum of, the sum of all these quantities, right? But the sum of, but each row, this number is just the sum of this, this, and this, right? So what we did was we took all the numbers in this 3 by 6 square rectangle, right? And we said, let's add to the left like this. So we got 1, 0, 0, 1, 1, 3. And then we added going down like that, and we got 6. 3, 1, 1, 0, 0, 1. Okay, so another way of saying this is we just took all the numbers in this rectangle and we added them up. Right? So we added how many people got back their homework. So, it was just the sum of everything in this rectangle. And we said, one way of adding up everything in this rectangle is you just add to the left, and then you add down. Okay, but addition is commutative. You can add in any order that you want, right? It doesn't seem very dramatic or, very remarkable, because you've been doing this since you were, yeah? But it's a remarkable fact. It's a very powerful fact that you can add in any order that you want. And this is the only thing that we are using in linearity of expectations. We are saying, you're free to add in any order that you want. So in linearity of expectations, we say, well, look, if you want to add up all these things, let's add each column first, and then we'll add up the results here. So we add each column. What do we get? We get 2, 2, 2, right? Which is meaning that the expected value of x sub I is 2 over 6, 2 over 6, 2 over 6. Why is that? Well, x sub I is 1 if the ith person gets their homework back. There are 3 people, there are 3 possible homeworks. What's the chance that this particular person gets back his own homework? It's 1 over 3. So this was easy to compute. And then we can add across like this, and we get the same answer, 1. So that's all linearity of expectations is. Right? It's just saying you're adding together a bunch of numbers. It doesn't matter which order you add them in. Let's find a convenient order in which to add them in. And that's these random variables. And so that's it. Okay? This makes sense? Yeah? Helpful? Yeah, okay. Okay, now, let's see, where are we going to? Okay. Okay, so now, let's talk about the last such, integer valued random variable that we'll talk about. That, this is going to be, this is called the Poisson distribution. Now, the Poisson distribution is either very confusing or really easy. So, hopefully, you'll find it really easy. Okay, so let's see if we can make it so that it appears to be really easy. Okay, so here's what the Poisson distribution is about. Here's one way to think about it. Okay, so what we are thinking about is a Geiger counter, right? So you have some radioactive decay, and every so often, a particle is emitted. Okay? And when it's emitted, you detect it, and then what happens? And then, whether you've detected it or not, doesn't change anything. It's a memoryless process. Right? The fact that you detected one particle doesn't mean that you won't detect one immediately thereafter. Right? So it's like coin flips. Okay, think of it exactly like coin flips. Okay, so the Poisson process is just like coin flips, except that now the coins are being tossed so frequently you can't even keep track of them. Okay, nature is tossing these coins sort of every femtosecond. There's no hope of even keeping track of this process. But on the other hand, the bias of the coin is very, very slight. So even though nature is tossing these coins every femtosecond, it actually emits a particle roughly once a second. Okay, so there are these rare events that occur. And so if it's emitting a particle roughly every second, then for our purposes, what we are thinking is roughly in a second we expect to see one such blip on the Geiger counter, one click, right? But it could be more. It could be that in this particular second we saw 2 clicks, or we heard 2 clicks, or maybe 3, maybe 5, maybe none, right? And so that's the process we are trying to understand. Does it make sense? Yeah? So I can repeat this, but this is something you should hold on to tight, because then we'll get into the formalism, and it might again start seeming a little iffy. So this is the place to catch hold of the concept. So if you hold on to this, it's easy, and then everything will make sense. Yeah, is everyone okay with this? Okay. Do you want me to say it again? Yeah? Yeah? Okay. Are there an equal number of people who, if I say it again, it'll just knock it out of their heads and then they won't know anything? No. Okay, no, okay. So let me say it again. Okay. So here's the process. Okay. So the Poisson distribution has to do with it's again coin flips. Okay, coin flips are going on in the background, but there are so many of them we can't keep track of them. And then the other thing about the Poisson distribution is that these coin flips that are going on in the background, they are mostly unsuccessful. Right? The probability of heads is so small. So think of the number of coin flips as going to infinity. N is going to infinity. But the rate at which heads occurs is fixed. Right? So if you do n flips in 1 second, then the chance that you get a heads on any one flip is 1 over n. Okay? So now think of n as becoming larger and larger, and the probability of heads is 1 over n, so the number of times you succeed in getting a heads in a unit interval stays 1. It stays fixed. Okay? But obviously these are coin flips, so you know, in this particular second, you may get 1 heads, you may get 0 heads, you may get 5 heads. It's all the luck of the draw. So now the question is, how many heads do you get in 1 second? Okay? And so here's what the Poisson process says. Okay, so let's do it first with 1 click per second on average. And so now the probability x equal to I is going to be 1 divided by I factorial times e to the minus 1. Okay, so e to the minus 1 over I factorial. Okay. Why did we put in e to the minus 1? Well, you know, it's a probability distribution, so the sum of these probabilities should be 1 over all I. So if you add 1 over I factorial, yeah, it adds up to e. It's a it's a Taylor expansion of the constant e. E is this Euler, what's it called? It's Euler constant. Is that what it's called? E is what, 2 point something? I'm sorry, 2 point. Okay, 2 point what he said. Okay, so it's some constant like 2.7. Okay, so e is the thing that we take the natural log to. It's that constant, right? It's also the sum of the series 1 over I factorial I going from 0 to infinity. So, okay. So, you know, so this is clearly the right, you know, if the probability x equal to I is proportional to 1 over I factorial, then this is the right answer. Okay, now, what I told you is only part of the story. In general, it's not going to be 1 click per second. In general, the number of clicks per second is going to be some number, right? It's some observed number. It's some observed rate at which you're seeing radioactive decay. So let's say that you have lambda clicks per second on average. So then the probability x equal to I will be lambda to the I divided by I factorial times e to the minus lambda. Okay, lambda is just some constant. It's like 1 or half or 2 or 3. Okay? So you pick lambda. Lambda is what you observe. Okay, so does this make sense so far? Yes?
Can you say once more what it's saying?
What is x? Yes. So let me just add 2 words here. 1 click per second on average. Okay, so this is called the rate. So lambda is called the rate. Okay? So this is the rate at which you're observing these clicks. And now, if you're observing these clicks at rate lambda, and now, you know, you've been observing them for a while, they've been at rate lambda, and now you want to know, you have a unit interval coming up. You want to know what's the probability that you'll see 0 clicks. Okay? So you'd substitute. What's the probability x equal to 0? So x is the number of clicks in a unit interval. Right? So you'd substitute. What's the probability x equal to 0? It's lambda to the 0 over 0 factorial. So lambda, that's 1 over 1, e to the minus lambda. So e to the minus lambda is the chance that you'll see 0 clicks. Okay? So if you want to know what's the chance that I'll see exactly 1 click, so you'd substitute 1, you'd see lambda to the 1 divided by 1 factorial, so it's lambda times e to the minus lambda. Okay? So probability x equal to 0 is e to the minus lambda probability x equal to 1 is lambda times e to the minus lambda. Probability x equal to 2 is what? It's lambda to the 2 over 2 factorial e to the minus lambda. Okay. Probability x equal to 3 is lambda cubed with 3 factorial, 6, e to the minus lambda. Okay, you get the point, right? Yeah.
And the expected value of this distribution has to be lambda?
The expected value is lambda, yes. So we'll calculate it. Okay? Yeah, good point. So we need to calculate the expected value of this distribution. Should we calculate the expected value? So the expected value of x is summation over I equal to 0 to infinity, I times probability x equal to I, which is summation I equal to 0 to infinity, I times lambda to the I over I factorial e to the minus lambda. Which is summation I equal to 1 to infinity. Right, 0, it's 0, right? And so we can cancel an I. So we get lambda to the I over I minus 1 factorial. Just canceling i's, e to the minus lambda. So we can pull out a lambda, pull out e to the minus lambda, summation j equal to 0 to infinity of lambda to the j over j factorial. Oh, sorry. Right, do you see what I did here? So I just said I is going from 1 to infinity, so I can let j equal to I minus 1. So I have j factorial, lambda. I pulled out 1 lambda, so I got lambda to the I minus 1, which is lambda to the j. Maybe I didn't want to pull out the e to the minus lambda. Okay. So now what's this? This is lambda times summation j equal to 0 to infinity of the probability x equal to j. Right? So this has to be equal to 1. So that's all lambda. Right? This is, this expression was just the probability x equal to j. And so, if you're summing up what's the probability x equal to j over all values of j, that's got to be equal to 1. So we can sort of verify that. Okay. Okay. So let me just give you a piece of advice about this calculation. So there are 2 ways you can handle it. Either you can follow it, or you can say, there was a calculation, it checked out, the expectation is lambda. Okay. Okay, so here's what the Poisson distribution looks like. Of course, it's I've drawn it as a continuous curve, but of course it's it takes on these different values. So these are the different values of lambda, and then these curves are supposed to represent, of course, the values are only at these integer points, but we've just smoothed them out. So what you can see is that it looks sort of like the binomial distribution, which is what it should, because we are, of course, thinking that behind the scenes there are coins being tossed. Right? Many, 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 many coins being tossed. It's just with a very small chance of heads. Okay. Okay, so let's do a couple of examples. So here's a first example. Sorry, this first example corresponds to this. So it's this particle example. So suppose you have, you're seeing radioactive decay. You're seeing 2 particles being emitted per minute, per second. So the rate lambda equal to 2. I guess lambda equal to 2. Okay. And now what we want to know is what's the probability that you see 3 particles? Right? And you can do that by just computing, right? The chance of getting I particles is just lambda to the I over I factorial e to the minus lambda, which is 2 to the I divided by I factorial e to the minus 2, right? Because the rate is 2. And then if you compute it, you can just work it out for different values of I equal to 0, 1, 2, etc. And those are the numbers. Right? So you can see it starts off low, it goes up, and then it comes down. Right? It's like the binomial distribution. It sort of goes up and then comes down. Yeah? Okay, so the Poisson distribution is extremely interesting. It's extremely useful because, it sort of shows up whenever you have these rare events, right? So if you want to know the number of missed calls, right? So you have many, many callers on a network. You want to know how many people miss calls. Well, or how many errors are there? These sorts of things. These are all sort of many such things are modeled by the Poisson distribution. So whenever you have a large number of entities, you have a huge network of computers, and you want to know how many failures are there. Well, hopefully you've designed your network so that the number of failures is small. But then, on the other hand, there are many, there are many servers, there are many, there are many computers, and so you have a certain rate at which failures are occurring. And then you want to know anything about the probability distribution, you use the Poisson distribution. Right? So it's used all over the place. Okay. So it's used in so many places that, well, let me tell you the way it was actually, the very first application of the Poisson distribution. Okay, it was done by somebody named. Okay, this is the name. I don't know how to pronounce it, so I'll write it down. When you have RTK in quick succession, you know that you're in trouble. So, and we haven't even gotten halfway there. Okay, anyone know how to? If okay, I'm sorry, I can't do it. Okay, so this was back in 1898 when they were much better at pronouncing names like this. So what he was trying to do was calculate, try to figure out something about, what were the chances of a soldier getting killed by being, because he was kicked by a horse. Okay? So this is, these are rare events, hopefully. But in fact, they were less rare than you would think. Okay, so what he did was he collected data for for 10 cores. So there were 10 different cavalries over 20 years. So it's as though, he had data, about 200 years of data. 200, core years of data. Right? And what he found is that there were 122 deaths. I mean, that's a respectable number. I mean, maybe this wasn't the leading cause of fatalities, but it was up. It was not trivial. So the way he modeled it was as a Poisson distribution. So now, okay, so now imagine, put yourself in this guy's shoes, and he was trying to figure out what's the chance of getting, what's the chance that there would be 5 deaths in a year, right? In a core. And how would you figure this out from this data, right? It seems impossible. Right? Except once you have the Poisson distribution, it's a piece of cake, right? Because what do? You divide 122 by 200, that's your rate, right? So lambda equal to 122 divided by 200. And now ask any question, and you know the answer to it. Right? So, what's the probability there would be no such deaths? Oh, you just figure out it's e to the minus lambda, whatever, right? So, oops. So here's the. Okay, so here are the probabilities of 0, 1, 2, 3, 4, 5, 6 deaths per core per year. So it's 0.54, 0.33, 0.1, etc. Now let's go and figure out how closely it matches the actual data, right? So you have to multiply this probability by 200 to get the number of deaths. So assume that it was actually Poisson. So he had data over 200 core years. So if this was the probability per core year, then it would be times 200, and this would be the number of deaths during that period. This was the actual number from the data. So you can see it's extremely close. The fit is very, very close, right? So this is why the Poisson process is such a powerful concept, right? And this is why you'll find it useful if you understand it. Yeah? Okay, so shall we do one more thing? Okay, one more thing. Shall we compute the variance of x? Okay, what was x again? Remember what was x? Okay. So we have a Poisson process with rate lambda, right? Meaning the expected number of, well, if it was particles, number of clicks of the Geiger counter is lambda per unit time per second. And now we want to know x is the number of clicks we got in 1 second, a unit interval. Right? So it has some probability distribution. We know the expected value is lambda, but now we want to know what the variance is. Okay, so we want to know the expected value of x squared. Actually, what's the variance of x? Let's figure out. What's the variance of x? It's the expected value of x minus mu whole squared, where mu is the expected value of x, right? And then we computed this formula for the expected value for the variance. It was the expected value of x squared minus the expected value of x whole thing squared. Yeah? or mu squared. Yeah? I'm sorry. Sorry. Oh, yeah, you're right. Okay, so here, I didn't need to use mu. I could have just used, I could just have said the expected value is lambda. Okay. To use fewer Greek letters. Yeah, good. Okay. So now from that formula, all we need to do is figure out the expected value of x squared. Okay, that's all we need to do. How hard can that be? Okay, so let's compute expected value of x squared is summation I equal to 0 to infinity of I squared times the probability x equal to I, which is summation I equal to 0 to infinity I squared times lambda to the I over I factorial e to the minus lambda which is summation I equal to 1 to infinity. We can cancel one of the i's. So we have I times lambda to the I divided by I minus 1 factorial e to the minus lambda. Okay, now we want to cancel off the I minus 1 from here. So we're going to break this up into two pieces. So we'll write, and then should we let j equal to I minus 1, is it? J equal to, so we'll go summation j equal to 0 to infinity. Oh no, let me not do that. Okay, I can't keep track of all this in one shot. So let's see. So this is summation I equal to 1 to infinity of I minus 1 times lambda to the I over I minus 1 factorial e to the minus lambda plus lambda to the I e to the minus lambda over I minus 1 factorial. Yeah? Now we let I minus 1 equal to j. So you get summation j equal to 0 to infinity. J, so we can cancel this. So we get j minus 1 factorial. We can pull out lambda squared from here. Lambda to the j e to the minus lambda plus over here we pull out lambda times summation j equal to 0 to infinity lambda to the j e to the minus lambda j factorial. Okay? So each of these is 1. Right? This is just the summation probability x equal to j. Oh, sorry. What did I do here?
Should it be lambda, not lambda squared?
Yeah, no. Okay, sorry, this was j minus 1. So this would be j equal to 1, 2. Okay, so if you work it out, these both will end up being 1. Okay, and you'll get lambda squared plus lambda. Okay, so you'll get expected value of x squared is lambda squared plus lambda. Take my word for it. If you work this out, this was exactly the thing that we went through the last time when we were computing the expected value of x. So this will turn out to be 1. That was 1 very easily. So you'd get lambda squared plus lambda is expected value of x squared. Now we have to compute variance of x. We take expected value of x squared minus lambda squared. Right? So variance of x is now lambda squared plus lambda minus lambda squared, which is equal to lambda. So when you have a Poisson distribution with rate lambda, the expected value of x is lambda, and the variance is also lambda. Okay? So if the variance is lambda, so let's say lambda was 2, let's say lambda was 4, right? The variance is also 4. So the expected value is 4, the variance is 4. What does that mean? The standard deviation is the square root of 4, which is 2. So so the expected value is 2. You expect it not to deviate too much from 4. You expect it to be plus minus 2. Okay. And now, if you want to know what's the chance that it's not 2 away but 4 away, you can use Chebyshev's bound, and you can say the probability will go down quadratically in the number of standard deviations that you go away. Okay. So, all right. So that's it. That's as far as probability distributions.